Thanks. Hi, everyone. So my name is Matteo, and today with Dong, we will present to you query processing on Tensor Computation Runtimes. Okay. So I will start off with some background and motivation for the project. So basically, the motivation is around the massive investment that is happening on deep learning in the machine learning community. So if you look at from the research point of view, basically we can see that there's been a lot of work going on kind of the amount of papers that have been published by the machine learning community on deep learning topics. So this chart is a little bit old, but as you can see, like in 2019, there were published around 100 papers per day on arXiv, which is kind of massive. And of course, all this production from the research point of view are translated into new neural network architectures. And as you can see here, every new generation neural network architecture basically require new resources, both on the computation point of view and on the memory point of view. And as you can see, basically the amount of resources that are needed is growing exponentially. So because of this, basically then happen a lot of investments on hardware related to machine learning. So you can use CPUs, but most of the investment are happening on GPUs by AMD, NVIDIA, and of course on FPGAs or custom ASICs such as the TPU, for instance. Basically, if you look at the, and this is just for the kind of the big companies, but there are also a lot of startups that are kind of popping up in this domain. So you can look at the graph cores, Cerebra, et cetera, et cetera. So in general, if you look at this analysis on the amount of money that been poured on the new hardware specialized for the machine learning, basically they were saying that venture capitalists alone, they're putting $2 billion a quarter with the goal of reaching around 200 billion. The total market will reach 200 billion around 2025. So in general, the amount of money that is poured into this space in the hardware for machine learning is massive. But of course, it's not just about hardware. So hardware alone kind of is not that useful if you don't have proper software that support it. And we've seen a lot of new software tools happening that allow basically data scientists, machine learning practitioner to implement their model easily and deploy them as well on this new hardware. So there are the usual suspects such as PyTorch and TensorFlow, our own Onyx Runtime from Microsoft, and like startups like a TVM that allow you to compile your machine learning model for the hardware that you have. So if you look at on the database point of view, if you switch a little bit gears, the situation is a little bit different. So we have been exploring hardware acceleration for databases, of course, but the amount of investment that is happening on our field is definitely more modest. And basically the problem here, as you know, is basically that you have to port part of your databases on the different hardware that you want to support. So it's an n time m, we call it an n time m problem. So if you just look at your relational operator, for instance, if you want to run your relational operator on a different hardware, you have to port your implementation on a different hardware. And this is really hard and engineering heavy. So the core idea of this tensor query processing is to basically try to leverage the infrastructure that have been built by the machine learning community for deep learning. So basically, if the neural nets, you basically implement your neural network using PyTorch, TensorFlow, and then you can leverage this open source ecosystem to basically run your machine learning model on any hardware that you want. So our idea is pretty much try to see whether we can consider these tensor computation runtimes not as tools just used for machine learning to implement your machine learning model, but as a generic compiler for hardware accelerators. And specifically in this case, we try to see if we can be used as a compiler for SQL queries. Why do we even think about something like this could work? So we actually had a little bit of experience in the past few years. We've been working on translating classical machine learning models such as gradient boosting trees, decision trees, and one-hot encoding. We're using a similar technology over PyTorch and then run it over CPU and GPU. And we have quite been successful on this, and the tool is called an Hummingbird. It's actually open source, so you can check it out. And last year at VLDB, we presented a work where we showed that we can do the same also with graphs, algorithms such as PageRank. So basically, the pro and the cons of this tensor query processing is that we can leverage the massive investment that is happening in the specialized hardware for machine learning, also for databases. And our approach, we claim that is scalable in the sense that as long as you can crack the problem of implementing relational operators using the Tensor API, you pretty much can leverage this open source system to run your query over the different hardware that they support. So of course, there are several open questions. So is this even possible? What are the performance implications of this, and how expensive, kind of engineering-wise, is this going to be? And now Dong will go over the details of the system. We'll answer this question.
Thanks, Matteo. Hi, everyone. I'm Dong He from the University of Washington. Now let's dive into the details of tensor query processing. The input to the system is a SQL query using the Spark SQL syntax. The system takes the SQL query and in this parsing layer converts it into an intermediate representation graph, or IR graph, that represents the query's physical plan, which is generated by Spark. Then the canonicalization and optimization layer takes the IR graph and performs IR to IR transformation and simple rule-based optimizations. The optimized IR plan is passed to the planning layer consisting of operator implementations in PyTorch. In this layer, each operator in the IR graph is mapped into a tensor implementation. For example, tensor implementations for sort, for join, and for filter operators. Finally, the execution layer generates a program using the operator plan that will run at query time on the target tensor runtime. So we can choose to run on different targets like Onyx, PyTorch, TVM, and etc. And once we have a target runtime, we can basically target any hardware that this runtime supports. We call the system we built Tensor Query Processor, TQP. TQP represents relational data in a columnar format with virtual IDs. For example, numerical columns are represented by n/1 tensors. For the interest of time, I'll only show you examples of the filter operator implementations using tensor computations. For this filter condition, we use LT, which is the less than operator, to implement the filter condition. It generates a Boolean mask, which is then used as a parameter of the masked select operator to generate the filtered version of the L quantity column. Another option would be to use indexes to extract the values satisfying the condition. This is known as the selection vector implementation. Here we use the non-zero operator to extract the selection vector, which contains the indexes of the valid rows. Then the output of the filter would be the rows whose indexes are in the selection vector. I invite you to read the paper for more operator implementations, such as joins and aggregations and so on. Now let's try to answer the open questions we have one by one. Is this even possible? So TQP implements all common relational operators with tensor operations, selection, filters, join, including non-equi join, group by aggregates, and so on. The operators help TQP to support all 22 TPC-H queries. The common tensor operations used in TQP are shown here. There are several, there are simple ones like addition, subtraction, and also complex ones like unique, bin count, and scatter. Now we can answer this question positively because TQP supports the full TPC-H benchmark. Now the next question is, what about TQP's performance? The table shows the query execution time in seconds on TPC-H benchmark at scale factor 1. We have TQP in two modalities, interpreted, which is TQP in the table, and compiled using Torch script, which is TQP-J in the table. And both numbers highlight the best performance for CPU 1 core and GPU. On CPU, if we compare TQP and Spark, we can see that TQP outperforms Spark for most queries. Given that TQP uses the same query plan as Spark, this suggests that the tensor abstraction is indeed good enough for executing relational queries. If we then compare TQP and DuckDB on CPU, DuckDB clearly outperforms TQP. This is because TQP's query plan is not as good as DuckDB's. I'll show you in a moment with better query plans generating better tensor programs, TQP can match and outperform DuckDB on CPU. Finally, we'll look at the GPU results. We compare TQP with Blazing SQL and OmniSciDB. We can see that TQP outperforms Blazing SQL for all queries, and it also outperforms OmniSciDB for 15 out of the 18 queries supported by OmniSciDB. TQP also has better query support because it supports the full benchmark, while Blazing SQL and OmniSciDB only support 17 and 18 queries respectively. Let's now look at larger data sizes. We scale the data set from 1 gigabyte to 10 gigabytes and compare the query performance over several representative queries. In general, on CPU, we see that TQP, which is the orange line, scales not well for almost all queries. On GPU, TQP is the red line. And for Q2, Q6, Q14, and Q18, TQP on GPU performs the best among all systems. For Q1 and Q9, OmniSciDB has the best performance. This is because TQP's aggregate implementation uses sorting heavily, while OmniSciDB uses hash-based implementations. We now provide a dollar cost performance analysis of TQP on GPU compared to DuckDB on a CPU-only machine. So each subplot is a TPC-H query at scale factor 10. The y-axis is the TQP query time speed up over DuckDB on the CPU machine. The x-axis represents the machines with different GPUs. The dashed line in the plots are the speed up required for TQP on GPU to be more cost-effective than DuckDB. In other words, the bars have to be above the dashed lines for the query time speed up to justify the dollar cost increase. So TQP's GPU execution is more cost-effective compared to DuckDB running on the CPU-only machine for 16 out of the 20 shown queries for the T4 GPU, and for 9 of the 20 queries for the P100 GPU, and for 8 of the 20 queries for the V100 GPU. We now study whether TQP's performance can be improved with better query plans generating better tensor programs. To understand this, for a few queries, we hand-optimize the tensor programs similarly to what a reasonable query optimizer would do. For example, avoid sorting over already sorted columns. And we have 3 modes for TQP: interpreted using PyTorch, JIT compiled using TorchScript, and using TVM for code generation. The table shows the query time at scale factor 10. Both numbers highlight the best performance for CPU 1 core, CPU 6 cores, and GPU. On CPU 1 core, with the hand-optimized plans, TQP's performance is now better than DuckDB, while TQP was slower than DuckDB without the hand-optimized plans. On CPU 6 cores, TQP improves to be faster than DuckDB for 2 out of the 4 selected queries with the hand-optimized plans. On GPU, TQP still has the overall good performance. For Q9, TQP's query time improves by 4x while using the hand-optimized plans. For the interest of time, I'll skip the details of this experiment, but the takeaway is TQP can accelerate queries mixing machine learning and relational operators end-to-end using a unified runtime. We can now conclude that the performance of TQP looks great. Now, the last open question, how expensive is it going to be engineering-wise? Beyond the GPUs we showed that TQP can support, TQP also supports other backends and hardware as well. For example, integrated GPUs and even web browsers. And we achieve this with orders of magnitude fewer lines of code required compared to other systems that don't support all this various hardware. So the last open question is answered. TQP requires less than 8,000 lines of Python code. In conclusion, we presented tensor query processing so that we can enjoy the massive hardware and software investments made for machine learning. Our system's performance looks great while only incurring low engineering costs. I invite you to come to our poster today and demo tomorrow. Thank you. We're happy to take questions.